Hello, everybody. Welcome to today's webinar, Intake Manifold Sealing. Thank you for joining us. I am Amanda Harmony, and I am an admin assistant here at AERA, and I will be hanging out in the background, helping answer questions and moderating today.
Hey everyone.
Joining me today. Yep, go ahead, Rob.
Sure, sorry. My name is Rob Monroe. I look after membership and technical development here at AERA. And like Amanda mentioned, we're both going to be in the background answering any questions you've got, as well as we'll have some time at the end for when Brian's finished his webinar. We'll also be able to answer any of the questions that you have. And Amanda's going to show you how to use that questions box.
Hi, everybody. I'm Brian Roberts. I'm a technical specialist here at AERA. I and others here take technical calls. For our members, we do engine research and write technical articles for our Engine Professional magazine. And today we'll be discussing intake manifold sealing. So welcome.
All right, thanks, guys. Now, before I hand things over to them, I'm just going to go over a couple housekeeping slides with you. First off, there are a couple different ways to listen in to today's event. The first is to dial in via telephone. If you do that, make sure you select the appropriate button and enter your access code and audio PIN. This just makes sure that there's no background noise during the presentation. And the other way is to listen in via your computer's mic and speakers. And again, just make sure you select that appropriate button. A couple other things to know. There is a little orangish box with an arrow in it. This is your grab tab. This allows you to clasp and expand your control panel during the presentation, so it's out of your way while Brian's going through his presentation today. And then the last item is the questions box. If at any point you have questions, comments, concerns, anything, go ahead and type it in there, and Rob and I will be in the background getting those answered for you. So at this time, I'm going to hand things over to Rob, and we'll get going with this portion of the presentation.
Super, thanks, Amanda. So for those of you that are joining the webinar today that are unfamiliar with who we are or what we do, AERA is a network of engine professionals that have been around since 1922. So we've been around a very long time. We're made up of engine builders and rebuilders, installers, the parts supply manufacturers, as well as distributors. We have manufacturers reps that are members, schools that are members, government agencies that are also members, and we're made up of over 2,000 members worldwide. Now, just like the slide sort of states here, even back, our ancestors believed that networking was still a big part of how we learn from each other. That is exactly what we're doing today. AERA helps to create opportunities where we can get together and network. We do things at the PRI show, at the SEMA show, any of our tech and skills conferences or our regionals, and even our webinars. I mean, it's just, again, it's just the opportunity to get together, network, and learn from each other, and we really promote that here at AERA. Some of the member benefits for those of you that are not members of AERA, we do have our specification manuals when you do join for membership. There's 7 in total. So we have a cylinder head manual, we have cylinder block, connecting rod, crankshaft, failure analysis, flywheel. So these are all part of when you do join AERA, you do get those manuals. We also get a subscription to Engine Professional magazine. You've got your access to the toll-free tech line, automotive machine online training program. Now, AERA has an engine machinist and cylinder head machinist training program that is online, and we go ahead and it's just like a diploma-like looking certificate when you're all finished. We have that as well. We've got our Contingency Connection Engine Professional Rewards booklet. And that's a booklet you get when you join AERA that's loaded with all kinds of discounts and coupons from other manufacturers. As well, you do get a discount and a coupon to even join AERA in that booklet, as well as you can use that for Process Pro software as well. We've got special discounts from our AERA corporate partners. We do have corporate partners. We have 8 of them that offer discounts like on freight packages. We've got things like credit card discount processing fee packages and that sort of thing. So something to look into there. We've got our Process Pro specification software. There's over 9,000 engines listed in our Process Pro software. So that's another benefit. When you become a member of AERA, you have the opportunity to use that software. Then new to us is a custom training program. Chuck Lynch, who's one of our other techs, heads up this program, and he can come right to your shop. And sometimes you just need help with training some employees on a piece of equipment. Maybe you don't have time to do it yourself, and Chuck can help you with that. Maybe you've got some new work that you've got in the shop that you're unfamiliar with, and you need help on figuring out a process for doing that work. And Chuck can help you with that sort of thing. So if you any more information on any of these programs, you can ask at the end, or you can put it in the questions box. We'll help you out there, or you can get a hold of us and we'll also help you out with any of that stuff. Like I mentioned before, Brian, who's doing our webinar today, he is one of our techs on the Tech Center, including myself. We've got Steve Fox, Dave Hagan, Chuck Lynch, and all 5 of us do work the tech line throughout the day. We're open from 7 a.m. to 6 p.m. Central Time, so lots of coverage there for the tech line. The biggest thing about being a member of AERA is we want to help you succeed and make money. And if you allow us to do all of your engine tech lookups and specification lookups, it keeps you from having to come off the shop floor, and we can do all that, look up all that information and help you with that stuff. So again, we encourage that. You can fax us, you can phone us, you can go ahead and email us, however you prefer to get a hold of us. And again, let us do all that information lookup for you, and you're better off on the shop floor making money. So that's what we look after for you. Just a quick recap before we get into Brian's webinar. To be a member of AERA, a typical 1 to 3 employee shop is $3.99. And if you have your contingency connection coupon, you're only $3.24 for the year, or you can break it up into a monthly payment of $29.08. So it really is inexpensive to be a member. You do get unlimited access to the tech line as well as all the other member benefits that I showed you earlier. So it's very good value, and it's very worthwhile. So we're going to jump into the webinar today, and our presenter for today's webinar is Brian Roberts. And like I mentioned, he is one of the voices you'll hear on the phone when you talk or when you phone into the tech line. Brian's got over 20 years experience with product development and engineering for both Felpro and Dana Corporation. So very experienced, and we're looking forward to today's webinar. How's it going, Brian?
It's going good. Good morning. Good morning, everybody. All right, so today we're going to talk about intake manifold sealing and kind of run through the different types of constructions that are common today, kind of like a history of it, why the gaskets are designed that way, how to install them, what to look out for. Just give you a general overview of how to seal an intake manifold. So intake manifold gaskets, they come in a variety of constructions, but we're going to talk about a few of those constructions. They've changed and improved over the decades. Obviously, engines have been modified and improved over the years, so the gaskets have to go with it. So some of the common gasket constructions that we have today are fiber gaskets, molded rubber gaskets, MLS, and RCM. These different types of constructions varied due to several factors. The vehicles early on had rougher surface finishes than they do today. They required a little more conformable seal. That's why you had like a fiber-based, or the old, even before that, felt to seal engines. Those early engine manufacturers didn't have to be concerned with extended warranties that we see today. So the gaskets did not last as long, and they didn't need to. The engine designs changed. They included plastic manifolds. Those plastic manifolds require a different type of sealing element, to try and accommodate some of the characteristics of plastic manifolds. So as the changes in the automotive industry occurred, the gasket manufacturers needed to develop products to match those changes. So first, early style gasket, I should say, fiber gaskets. It's kind of broken down into like 3 sections for us here. So we have 3 most common constructions in use today. We have the fiber blend, which is just plain what people call paper gaskets. Fiber blend with a bead on it. So what you see over here is this little bead that's put on top of the surface of the fiber material. And then you have a solid core with the bead on top of it. So this little black area here represents like a steel core, basically. Let's see. All right, so typical on the early gaskets here, people call them paper gaskets, which it's not really paper. These are specifically designed fiber and binders combined together to handle different mediums like the coolant, the fuel, or combination of all of them with oil. They come in different thicknesses, so thinner materials. They have less conformability, but you get less relaxation and torque loss when you use the thinner materials. You use thicker materials, you get more conformability, obviously you get more torque loss, but they're available to accommodate more out of flat conditions and rougher surface finishes. So the fiber gaskets are usually produced with rule dies. So if you've ever seen a gasket operation, you'll see these rule dies being blanked on punch presses and blanking out shapes like you see down here. Like this, I believe, is a Chrysler 440. So all of these type of gaskets should be installed dry unless otherwise specified. Now, I know people like to put RTD on these things, and some RTD is okay. I don't recommend it, but you get people that think, hey, a little's good, a lot is better, and they smear it all over the place. That becomes a problem because then this gasket, when it's compressed, acts like a watermelon seed between your fingers. So you get that rubber coating on both sides, and when you squeeze it together, the gasket moves around. Well, it's only fiber, so fiber doesn't do well under extreme motion. It starts to destroy itself. So install dry unless somebody tells you otherwise. Okay. Then it came to the fiber with the beading. So certain applications needed a little bit more sealing capability in, say, an intake port there, or around the coolant ports here. At the bottom there, you see, typical small block Chevrolet intake gasket. So this screen printed bead, which is applied just like you would see a screen printing like a t-shirt, is applied onto the surface of the gasket, and the screen itself has different mesh sizes. So the mesh within the screen controls the amount of the beading material that's applied, and that allows for you to get a controlled height of the bead. The bead is then cured through either an oven with heat or UV, ultraviolet light. Typical bead materials: silicone, nitrile. What you're looking at here, the blue there, that's silicone. Typical bead heights anywhere from 2,000s to 6,000s tall. That bead gets embedded into the fiber material. So you see when the flange comes down and makes contact with this bead, it pushes it down into this material down here. And that densifies the material and provides a really good seal in that particular area. So over on the right here, you see not this particular gasket, but what we call a Fuji impression, which is just basically a film that indicates the different type of load that's seen when the gasket is clamped up. So if you're looking at the gasket here to the left, this particular grayish black material is the facing material, or the fiber blend. That would be like this area here. You see some loading here, and then this bead, the blue here, would be represented by this dark red line. So you would see a higher concentration of load right where the screen printed bead was placed. So the height of that bead is critical. If you don't have enough, you don't get enough load. If you have it too high, then that material gets compressed too much into this material here, and then it can end up splitting it, and then you have failure, leak path here. Okay. Then we have solid core fiber with the beading. So it's the same thing as what I just showed you previously, except for it has a steel core inside of it. That steel core helps with the radial strength that you see is needed sometimes on like the Siamese intake ports that you see on a small block Chevrolet. So you get that high vacuum, and that center skinny piece of fiber normally would try and pull in and get sucked into the engine. Well, with that steel reinforcement in the middle there, it doesn't move. So this again is that steel section down here, the fiber on each side, and the bead. And then here you can kind of see a cross section cutaway of the fiber with the bead going around, and then the steel and goes around it. These are kind of popular on some high performance engines because of that vacuum support there in that middle there. All right. Oops, sorry, went too far there. All right. Common failures with the fiber materials. Number one, low clamp load. Dirty bolts. It's important that the bolts be cleaned, wire brushed, get all of the rust and debris and dirt and grime off of there, because a dirty bolt will not produce the amount of load that you're expecting when it's torqued up. There's too much friction with all of the debris in there, and you'll get a lower clamp load than expected. Should put lubrication on there, the engine oil. That lubrication increases the coefficient of friction, which gives you better clamping, more load. So again, low clamp load is one of the common problems with it. Excessive flange motion becomes another issue. That low clamp load allows more motion. You got bimetal expansion. So if you don't know what bimetal expansion rates are, it's basically a condition caused by aluminum cast iron expanding and contracting at different rates. So as the engine heats up and cools, you've got aluminum that's expanding at a greater rate than the cast iron. So they're moving differently. And that causes just this minute amount of motion in the joint. So when you combine that flange motion that's normal with low clamp load, you'll end up scrubbing that gasket to the point of where the fiber will break down and create a leak path. So it's important to get that clamp load right and get that thing taken care of. So use of RTV or sealers. All right. Again, I explained earlier, some guys like to goop up the surface of the gasket with RTV, and some people are successful with it. Some people are not. So, I mean, if you're successful with it, I don't want to say you're doing it wrong, but, you know, we don't recommend it. So, and I can see I got a typo error there. Install dry. It's spray tack, not spay tack. Is okay to hold the gasket in place. Again, that RTV will cause flange motion or gasket motion in between that flange when it gets clamped up. Again, just picture yourself squeezing a watermelon seed between your fingers. And that's basically what you're doing with RTV on both surfaces. So install it dry unless otherwise told. All right. Newer engines today utilize plastic manifolds. So you need a material that's more conformable to that flexing or warping that you see on plastics. So molded rubber comes into play to solve this issue. So if anybody's been working on like an early style plastic manifold, say Ford 4.6 modular engine, that particular manifold, the early one on like a Crown Victoria, that guy would warp and unload the lower intake gasket at the coolant crossover area. And as that would warp, it would lift up and unload the gasket to the point to where the coolant area, the coolant crossover area would start leaking coolant. That particular manifold had other issues that would leak coolant, but basically the warpage of the plastic becomes an issue. So you need some kind of molded rubber that could try and keep up and accommodate that warpage. Now, not all gaskets are going to be able to accommodate warpage. I mean, excessive warpage, you're going to leak. So manufacturers have now looked at those intake manifolds and they've built in ribbing and other structures to stiffen it, and the warping has been minimized now. But the early style ones would warp So molded rubber was used to try and seal those particular engines. All the molded rubber products have what we call like a memory or recovery property that allows, as the flange moves, the rubber uncompresses and compresses and stays in contact with the flange. And that contact provides enough load to keep the seal intact. So molded rubber lends itself really well to producing complex three-dimensional shapes. So you can injection mold into these, mold cavities, all different types of shapes. So it gives creativity and flexibility to the engine designers on how they want to form an intake runner system, and then build in how we're going to seal it. So it works really well for three-dimensional shapes. Common molded rubber constructions. Here on the screen are some of the common ones. There's a whole lot more than this, but these are some of the more common ones. So you've got this press in place here. You've got edge molded. You've got what we call like encapsulated design, and you got void volume. All of these have a certain function and purpose, and we'll cover some of that here. Okay. Press in place gaskets. So press in place gaskets go into a channel that's in the intake manifold. So if you've looked at modern intake manifolds that are plastic, you usually see around the intake runner like a channel that goes all the way around it. And that channel is like represented right here. So you got this seal that you're looking at. This is the cross section of the seal. And this is looking at the seal from the top, just looking down. So you've got these little installation tab bumps here that are on the outside edges. That's what you see here, these little bumps here on each side of this seal. Those tabs, when you press this gasket into that channel, there's interference on the left and right sides here where that seal is grabbed now onto the manifold in that channel. And so when you go to install this particular manifold on the engine, you've got to flip it upside down or right side up, if you follow me, and set it down onto the engine. If you didn't have those interference tabs, that seal would just fall right out. You may not notice that it fell out, and then you bolt everything up, and now you've got a vacuum leak or a coolant leak somewhere, depending on what the seal is for. So once that gasket is clamped up, so if you look, this is the top of the gasket here. So you've got like a flange coming down that would hit the top of this gasket and compress it all the way to this surface right here on each side of the seal. Once that's clamped up, there's really a small cross-sectional area that's exposed to like an air-fuel mixture. It's really like a fuel vapor that's left over. But since the manifold hits this, or the cylinder head that hits this section of the manifold, it acts like a load stop. So now you can't over-compress the rubber. Over-compressing the rubber will cause it to rupture and split. So you can only compress rubber so much before internally it breaks apart. So as this flange comes down, hits that, bottoms out, you've got the perfect amount of load designed for the seal. So, here we see edge molded. Edge molded gaskets, they have like a rigid carrier. It's either steel or aluminum, sometimes plastic, but normally it's steel or aluminum. The sealing beads usually chemically bonded right here at the edge, or mechanically with like a dovetail around that would be cut out back here somewhere and then molded over there. So, and sometimes it's chemically and mechanically attached. So the benefit of this design is it allows you, for engines with a small area available for a sealing bead, to put the actual bead right up against where it needs to be. So for small land area type of flanges, this is a good design to use. The gasket carrier itself is a load stop. So when the gasket is put in and installed, this rubber and this side rubber are compressed to this thickness of the carrier, and then that provides the load stop so you can't over compress it. And then this particular bead height is based off of this thickness, so you get the right amount of compression on the rubber. As you can see over here, you've got an example of that. This is an aluminum carrier, and you've got this edge molded bead that goes around the whole thing here. Gasket gets clamped up, it bottoms out on this surface. There's your load stop. You're good to go. Void volume. This particular design allows rubber to be compressed into channels, which are basically voids on each side of this bead. So this bead here that we're looking at, you have voids on each side. So the gasket gets clamped up, bottoms out on this side and this side of this carrier. So this bead gets compressed, and then it has this void to be compressed into. So as it compresses, it expands to the left and right, and now you have material that a room for the material as it's compressed. So again, that the plastic acts like a load stop. So you clamp it up, you've got the right amount of compression on the rubber, you've got the positive load limiter in there, so torque loss is minimal. The issue we have with these is not supposed to put RTV on these. These are also installed dry. What we have seen is people put RTV all over this, thinking it's going to improve things, but what they don't understand is they just now filled each side of the voids on both top and bottom, which gives the rubber, when it's compressed, nowhere to go. So you try and compress all that rubber in there with no place to go, then you get a crack right through here, and it cracks the carrier. So RTV should only be placed on this particular small block Chevy down here at the corner where it meets the end seal on the V-style engine. There's no need for RTV anywhere else on it. So these type of gaskets, were common on GM and Ford engines in like the late 90s, early 2000s. Some of these engines had some issues with the extended life or OAT, organic acid technology coolants. That particular coolant would prematurely weaken the gasket. So the aftermarket now has improvements to this design that are available from different manufacturers. The gasket works, but it is susceptible to the extended life coolants. So, it's your choice if you want to continue to use that in a repair or not. Encapsulated designs. This is kind of like a replacement for that plastic intake gasket that you saw there just previously. So these gaskets usually have a rigid core, plastic, aluminum, or steel. It's surrounded by rubber. So you have all of this extra surface area to chemically bond the rubber to. So you've got a nice strong seal that can't pull away from the carrier. So on these particular designs, you've got molded in load limiters. So you've got a thinner carrier that's over molded, and then not represented here, but over to the left here, you would see a load limiter that's basically the same thickness as this rubber here coming out. And then you'd have that steel load limiter over here. And then it only allows the rubber to be compressed so much. And you've got the proper load that you need for the seal. These particular designs usually include extra beads. The extra beads provide insurance for pitting. A lot of these engines back in this time frame had what they call electrolysis issues, which was like a poor ground combined with a bimetal condition with the extended life coolants. You get all those together, and poor maintenance from the end user, not taking care of their cooling system, and you get this electrolysis, this chemical attack that would go after the weak link in the joint, and that is usually like the aluminum, manifold itself, and it would start pitting the manifold. And so you've got these extra beads on this particular design. So where the normal bead would be running would be somewhere over here on the plastic gasket. And now you have these extra beads that are outside of that area that can fill in the void, because usually that pitting occurs where the bead is in contact with the flange, kind of like you see on a crankshaft. You got that front crankshaft seal that rides on the shaft and it wears a groove in it. It's kind of like that, but it's pitting caused by electrolysis right where the bead was, and sometimes outside of that. And these extra beads provide that insurance to overcome that pitting. This particular carrier is an aluminized steel. Aluminized steel is nice because it's got corrosive protection from the steel, for the steel itself, so it'll last longer. This particular gasket here and competition's gasket has a specifically blended, I shouldn't say competition does, but this particular one has specifically blended an elastomer for the oat environment. So it's specifically designed to handle the oat coolants. I'm not sure if the competition has that or not. If it doesn't, it's usually a Viton, which is really good in coolants or fuel mixtures. Just like this one is a Viton, but it's a specifically blended one for oat. So it's definitely an improvement over the plastic, and I would highly recommend that if you're going to do the work, because the repair is expensive for these, that you just go ahead and put these on there and be done with it. So common failures for the rubber, again, the flange pitting from electrolysis. Here's just an example of a really aggressive pitting from electrolysis. You see all these little holes, little divots and craters in there caused by that electrolysis chemical attack there. Some people use JB Weld with a razor blade to try and clean that up. And they've been successful doing that. Other people, they just replace the head. So depending on the severity of the pitting, you machine it away, but you've got choices. Excessive warpage. Early design plastic manifolds, like we discussed, they warp over time, and that warpage unloads the seal and leads to leaks. The chemical attack. Oat coolants and fuels attack the rubber compounds if they're directly exposed. It breaks them down. So you got excessive compression set, which we'll cover in coming up slide here. Low quality elastomers with high amounts of filler that increase the compression set. So again, we'll cover that coming up here. Use of RTV or sealers. Again, using the RTV sealers causes gasket motion, fills in the voids on void volume stuff, causes fractures of that plastic gasket, and destroys the gasket. And I just can't recommend it highly enough. Install it, try, like the manufacturers say. Only use RTV at the joints or where specifically told to do so. And again, the traditional low clamp load situations. You've got dirty bolts, threads, lack of lubrication, things of that nature that lead to low load and leaks. One more thing on this that I'm just now thinking of is a lot of these earlier engines back in this generation, before E85 was out, you got people that try and utilize E85 gas in these engines, and those seals were not designed for that ethanol blend. And that particular E85 fuel will attack some of these rubber compounds that were never designed to accommodate it. So if your car is not E85, don't put E85 in it. You might think you're getting better fuel mileage or whatever, or cheaper gas, whatever you're thinking. but you're also exposing your car to some issues that are unnecessary from the sealing standpoint. So don't do that. Ooh, too far. Compression set. All right. So on all rubber materials, we have this phenomenon called compression set. So compression set is basically the amount of set the rubber takes after you compress it and its heat age. So you start with, say, a manifold flange here. You've got your free state void volume bead. So the manifold is clamped up and installed. Boom, you run the engine. The seal is compressed. It's heat cycled over and over and over. You go to take the manifold off for whatever reason, and then you're left with a little bit of recovery. So what you see here is you got the original height clamped up, unloaded, and now it's got this set that's now occurred. What you don't want to have is a set that is greater than 25% of the original height of the bead. All of these seals are designed to provide a specific amount of load to seal the fluid or the medium that's there. The engineers have, through testing, determined that 25% compression set is acceptable and still provide enough load to seal. You get above 25%, you're starting to get into the range of where the seal is not loading enough, and you're going to potentially leak, or the flange, say like on a plastic manifold, warps a little more than it should. Now the set is not allowing the seal to recover enough to make contact and provide enough load to seal. So there's an ASTM standard for this test. Basically, the rubber is clamped up in a fixture and it's placed in an oven for a specific time and temperature. The sample is removed and unclamped, and then they measure the difference from the original free state height and the post-test height and compare those two. And the difference, again, should not be more than 25%. So this is very important because I think on the previous slide we talked about fillers. Let's say you go and you buy a gasket set offshore somewhere, you got a great deal on it. Who knows if it's good? When I worked at Felpro and we did the compression set testing, we saw that some of our offshore suppliers had compression sets that were, higher than 30 to 40%. And that just tells us that the particular compound that they had was filled with ash or some other kind of filler that didn't have the properties that were significant enough to prevent the compression set. So you may save money buying a cheaper set somewhere, but like I said, you get what you pay for. So you got to be careful because the stuff may look exactly like OE or whoever, but it's not the same. And the amount of money you're spending to do a repair to get this thing sealed, I don't think is worth the risk. All right. Multi-layered steel is probably the more, or the newest, I should say, technology for intake manifold sealing. It's not very common. It's not used everywhere, but it's there. The MLS, if you're used to MLS head gasket, it's the same concept. You have multiple layers. So here's an example of a rubber coated layer here with an emboss in it. Then you have this distance layer in the middle, and then you have the same thing inverted here with another rubber coated layer here. These gaskets work really well, but they require a surface finish that's smooth. So the surface finish, what you see here, is 60 RA to 30 RA. So not quite as smooth as you see on a head gasket, but close. So if you have too rough a surface finish, you're going to run into problems with the coating not being able to seal the particular intake manifold, because the coating on each side of this material is very thin, and that's all that's used to fill the voids left from the machining process. So this coating thickness could be anywhere from 1/1000 thick to say 15 thousandths thick on like a RCM gasket, which we'll cover next, which is just a single layer rubber coated metal. But for MLS, it's usually very thin coating that's on each side. If you had too thick a coating with all these layers of coating here, 1, 2, 3, and 4, the thing would be really spongy and rubbery, and you'd have like a torque loss situation. You don't want that. So thin rubber allows for a nice tight joint without the spring effect that you get from really thick rubber. Now here's the rubber coated metal, which is that single layer that we talked about. Basically, it's just one layer of an MLS gasket, if you want to think of it that way. Again, not very common. It's usually used in upper intake manifold gaskets, plenums. Not as conformable to flange motion because you don't have the multiple layers acting as a spring. The surface vintage should be the same as an MLS gasket to ensure you fill the peaks and valleys. Sometimes you might get around a rougher surface finish if the coating is thicker. You could also replace this particular design gasket with a fiber-based product and be successful. You know, if you want to reduce cost for the end user, you can take that particular OE design and just make it into a fiber-based material, maybe with a core for the rigidity there, and cut down the cost. The gasket may not last as long as the OE, but you don't need it to normally. By the time this reaches, say, 100,000 miles, you only need the car to go another 50 or 60,000. You could use a fiber-based product for it instead and move on. Or you could just replace it with the OE style as well. But you have choices. Again, some of these RCM gaskets have thicker rubber coatings. This blue represents that coating, so that coating could be anywhere from 1 to say 15 thousandths thick. The thicker the coating, the rougher the surface finish. So you can do that. Here's a cross-section blow-up of what it means with the surface finish in this coating. So the coating in blue, you can see there, right here and here, and then this represents an exaggerated surface finish. So the surface finish has all these peaks and valleys, and then you can see the coating accommodates, and then the valley is too tall or too deep, and then there's potential leak paths. So this is why it's critical that the surface finish is to specification. If you don't have it, you're going to have potential leak paths. Okay. MLS RCM common failures. Again, we just talked about it. Incorrect surface finishes, probably the #1 reason why these guys fail. So too rough of a surface finish, again, causes the voids and the peaks and valleys. The coating's not thick enough to accommodate it. Too smooth, though, allows for gasket motions. So if you make it really smooth, you know, then you're going to have where the gasket can't be gripped by the little peaks and valleys enough, and then you have gasket motion, and you don't want that. You want an actual nice tight grip. Let the peaks and valleys grab the gasket and hold it in place. So another common issue that we see is scratches or debris in the gasket coating. So some of the earlier MLS gaskets had like a sticky coating, and guys would have a workbench that was dirty, had, you know, metal shavings on it, stuff like that, and they'd open up a kit, they lay the gasket on the bench, and then those particular shavings would be picked up by the gasket, and then they would install the gasket, and it wouldn't load properly because you had these little metal shavings or some kind of debris that was underneath and preventing it from being compressed all the way. The newer MLS head gaskets, the coating is not as sticky, but still the same situation can occur. It's still a rubber coating and things can stick to it or get caught in it if it's a little metal shaving. So, and even if it doesn't get caught, it could scratch the surface. So a scratch through a thousandths of rubber doesn't take much to take the coating off there. And then that's just a potential leak path. So when you're doing these installations, make sure the work surface that you have right there is clean. Take the gasket kit, open it up, leave the stuff right in the kit if you need to. But if you're going to take the gaskets out of the actual kit, make sure where you're putting it is clean and you don't have any issues with scratching or picking up debris. So low clamp load again, dirty bolts, they don't provide enough clamp load. Lubrication, you need that to pick up more load by lowering the coefficient of friction. So take care of those things. B engine sealing. Okay, so anybody that's been out there and has worked on a B-style engine, small block Chevy, whatever it is, the intake manifold sits on an angle, has angles to it that match up with the cylinder heads. Those flanges need to be parallel. So flange parallelism is critical. So you have even load across the entire gasket. I'm sure most of us have seen many times that the top or the bottom will be tighter on the cylinder head, which will have a lighter load on the top or bottom of the actual manifold gasket, which could become a leak path. So you need to look at flange parallelism to make sure that you have good contact all the way across the surface of the gasket. When you're doing the machining, as you take material away from like the deck surface of the head, the actual V dimension changes, and like your bolt holes for the intake manifold, they lower. They've just now moved down. So when you go to put the gasket on and then put the intake manifold, your bolt holes may not line up. So you may need to compensate by taking X amount off of the surface of the deck for the head, and then the face of the intake on the head as well to compensate for that. As you're machining and the manifold is lowering, now you're potentially over compressing the end seals that go on the front and rear of the engine, or what we refer to sometimes as the China wall. So to overcome that, a lot of guys use RTV right along that joint, just a bead of RTV from the feet of the intake manifold gasket itself all the way along the line of the wall to the other one. If you don't do that and you try and say use the stock cork rubber end seal or regular rubber end seal that might be there, now you're going to be over compressing that, and that's just going to spit out or split and cause a leak path. So as you machine and you lower that manifold closer, you've got choices. You either RTV that or you machine that wall as well to maintain the same distance between the top of, or the bottom of the manifold and the top of that wall. So the AERA, we have a technical bulletin on this machine. It offers all the different formulas that we need, or the machinist would need to compensate for taking X amount off of the deck surface, the face surface, and the wall surface to ensure that you've got the flanges parallel, you've got everything in line, and then you can provide the gasket with the best possible chance of success. So that technical bulletin is 1405. And that is everything in a nutshell. So I'd like to thank those who helped with the information for this webinar, and thank you for your time. Any questions?
All right, thanks, Brian. We had a few questions come in here.
Okay.
The first one for you is, what surface finish is needed for fiber gaskets?
Okay. Fiber gasket should be somewhere in that 30 to 60 RA range.
All right, and the next question
Mhm.
was, you say to install dry, but what about corners where the gasket meets an end seal?
Yeah, I think I covered that, but basically on that China wall or the front and rear wall of the block, and you got the head that comes down on a V, that joint there where the intake manifold meets that wall, that is usually where you put a dab of RTV there to connect the either cork rubber or whatever style seal is there. And it's just a dab of RTV, and it just fills that little void there, and that's all you do.
All right, perfect, thank you.
Mhm.
The next one is, can you reuse your rubber gaskets?
Okay. Some people claim that it's possible, and I've seen some people that haven't successfully done it, but it's not recommended. Again, you got to go back to that compression set that we discussed. The compression set that occurs in all of these rubbers gasket diminishes the recovery property of the seal and leads to like a low load condition. So I do not recommend it. Again, just like using RTV all over a gasket, some people are successful. It's not recommended. I can't say you can't do it. I'm just saying you shouldn't do it.
All right. And then the last question we have right now is, can you just use RTV to seal an intake?
Theoretically, yes. But more than likely, the RTV will get into the cooling system or into the valley and into the oil, because you're going to put this goop of RTV all over, and then you're going to compress it. And that RTV is going to go somewhere. And so once you compress it, it's going to go out the sides. And depending on how much you put on there, some of that could break away and get into, say, a cooling system and get into blocking a thermostat, damaging a water pump. Gets down into the valley, gets into the oiling system, gets picked up, gets into the oil pump area and causes issues there, blocks just the circulation of oil. Now you don't have lubrication, you wipe out the bearings, and a whole host of things that can go wrong. So theoretically, yes, you could do it, but I don't recommend that either. And if you try and take it apart, have fun, because it's going to be like prying off, or we call it grenaded off. It's going to be stuck. So, and it's going to be a mess to clean. So.
All right, well, thanks again, Brian, and we want to thank everybody for their time. If your question has not been answered yet, we want to make sure we keep this under an hour, so we will respond via email and make sure we get everyone answered yet today. When you leave the webinar, you will get a request to take our survey. Please take a moment and fill that out. Just let us know how we did, if you have any additional questions, comments, anything for us. You will also get a link tomorrow to a recording of today's webinar. You can use that to rewatch the presentation, share it with staff. It's yours to use at your disposal. And lastly, you'll see our contact information there, including the main line for AERA and our email addresses. So if you have any follow-up questions, you can email any of us at any time, and we'd be happy to answer them for you. Thanks again, and we hope everybody has a great day.
All right. Thanks, everybody.